Hello students. So we will continue with our NCERT chapter 7 of class 12, that is alcohol, phenols and ethers, and today is the theory part 5. So this is the disclaimer. So what is the objective of today's lecture? So when you will attend this lecture, you will be able to understand the preparation methods of phenols. In the previous lecture, we discussed that what were the preparation methods of alcohols. So today we are going to discuss the preparation methods of phenols. So for your reference, I have mapped the NCERT sections which we are going to cover. So we will cover section 7.4.2, that is preparation of phenols. And we will solve some in-text questions, that is 7.4 and 7.5. We will solve exercise question, that is 7.9 and 7.10. And then we will summarize whatever we studied in today's lecture. So let us start with the preparation of phenols. So I hope you remember that what are phenols. Okay, so it is an aromatic ring and one of the hydrogen is replaced by hydroxyl group, that is OH group. So in case of phenols, the OH group is directly attached to your benzene rings. Okay, so today we will see that what are the methods that are followed for the preparation of alcohols. Preparation of phenols. So there we will discuss today 4 methods for the preparation of phenols. So first method is from haloarenes, and this method is also called as Dow's process. So in this method we will see that how from haloarenes that we took as chlorobenzene, from chlorobenzene how we prepared phenols. Next is benzene sulfonic acid. So in this method we will see that how from benzene sulfonic acid we have got a phenol. Next is the diazonium salt. And the fourth method is from cumene. So one by one we will see all these 4 methods for the preparation of our phenols. So first method for the preparation of phenol is from haloarenes, and this is called as Dow's process. Now haloarenes means there will be one halogen which will be attached to your benzene ring. So what happens in this process? If we are taking example of a simple haloarene, that is a chlorobenzene, that is to your benzene a chlorine group will be attached. When this chlorobenzene is heated with sodium hydroxide, which is a base, at temperature 623 Kelvin and pressure 300 atmospheric pressure, then we will see that after acidification with hydrochloric acid, we will get our phenol. And if there are electron withdrawing groups like NO2 that withdraw the electron density from the ring, we will see that if these electron withdrawing groups are attached at ortho and para positions, so this increases the rate of this reaction. So let us look towards the process. Now this is a process. See, first we have a haloarene. In this case we have a chlorobenzene. So here a chlorine is attached to this benzene ring. And we have a base, that is sodium hydroxide, that is NaOH. Now we know that chlorine is a good leaving group. So being chlorine a good leaving group, it will take this hydrogen from here and HCl will leave. This chlorine will leave from this ring. Now we have ONA. So this is a nucleophilic substitution reaction. Okay, so this ONA will act as a nucleophile because there is electron density present on this oxygen, and it can donate it to this carbon because this carbon is now electron deficient. Why? Because chlorine left away with the electrons. So this carbon is electron deficient and your ONA group has the electron density on this oxygen. So this will attack on this position and you will get sodium phenoxide. What is this called? This is called sodium phenoxide. When O minus group is attached to the ring, we call it as phenoxide. And when this sodium is attached, we call it as sodium phenoxide. So here, what is happening? There is a nucleophilic substitution reaction. And see, the temperature is 623 Kelvin and it is at 300 atm. So chlorine will leave and ONA group will attach at this position. So this is sodium phenoxide. Now for making this to phenol, here sodium Na plus should leave and hydrogen should attach. So we will do the acidification. Means we need H plus group over here. From where we get H plus group? From acids, because acids donate your H plus ions. So we will do the acidification with the acid, and the acid which we are using here is hydrochloric acid, that is HCl. So that will break into H plus and Cl minus. And here I have O minus and Na plus. So this H plus will attach to this O minus and we will get phenol. That is, see, this OH hydroxyl group is directly attached to your benzene ring. And Na plus will attach to the Cl minus and NaCl will leave. And we got a final product, that is phenol. So this process is important process. That is how from a chlorobenzene we got a phenol. So first nucleophilic substitution reaction will take place. The nucleophile will attack on this electron deficient carbon from where your chlorine has left, and then we got sodium phenoxide. And then acidification will happen with HCl and H plus will attack on this O minus. So we'll get a phenol. So this process is also known as Dow's process. So this is the first method, that how from a haloarine we prepared an alcohol. Now let us see the second method. Second method is from benzene sulfonic acid. We will see that how from benzene sulfonic acid we are getting a phenols. Benzene sulfonic means on a benzene ring a sulfonic group will be attached, that is SO3H group. So see, your first we'll take a benzene. Okay, so first your benzene, it will react with oleum. Oleum is H2SO4 plus SO3. So first we will take a benzene, it will react with oleum, and then we will get benzene sulfonic acid. And then this benzene sulfonic acid is then heated with molten NaOH. So first we'll get benzene. From that benzene, we will get benzene sulfonic acid, and then that benzene sulfonic acid is heated with molten NaOH, and then this mixture is acidified to obtain the phenol. We will treat it under acidic conditions, that is H plus, and then we will obtain a product, that is phenol. So look at this process. I said first we are going to take a benzene. So this is a benzene ring. Then we will treat this with oleum or fuming H2SO4. So when we will treat it with oleum, we will see that we will get a sulfonic group over here. Now see this reaction, that from benzene, when we treat it with oleum, we get benzene sulfonic acid. This is a benzene sulfonic acid. This is an electrophilic substitution reaction. Okay, that means a electrophile will attack on this benzene and one hydrogen will be replaced by your sulfonic acid. So this hydrogen will replaced by this sulfonic acid. So this is a electrophilic substitution reaction. So from this electrophilic substitution reaction, from benzene, we got benzene sulfonic acid. Now see, this is an acidic group, that is SO3H. Now acidic group, how it will break into H plus and SO3 minus. Next, this acid will be treated by a base. We will treat this acid with NaOH. So your base gives hydroxide ions, that is OH minus and Na plus. So this is SO3 minus. So Na plus will attack on this acid, that is SO3 minus, and you will get SO3 minus Na plus. That means acid is reacting with the base and a salt will be formed. When acid reacts with the base, then a salt is formed. So when this base will react with your SO3H group, which is an acidic group, you will get SO3 minus Na plus. Okay. Now again 2 moles of NaOH will further react with SO3 minus Na plus, that is with a salt, and then your Na2SO3 and water will leave. So you will be left with O minus Na plus. Now this is similar to the Dow's process which we studied. So we are left with O minus and Na plus. And further we will treat it with we will treat it with acid. We will do the acidification. So H plus will attack on your O minus Na plus. So O minus is there, so H plus will attack and it will form phenol, that is OH, and your H plus and your Cl minus will leave in this condition. So you will be left with a phenol. So this is how from a benzene, first we got benzene sulfonic acid, and then from benzene sulfonic acid we got a phenol. So this is another method of preparation of phenol, that is from benzene sulfonic acid. Next is from diazonium salts. We will see that how from diazonium salts we are preparing our phenols. So first, in case of diazonium salts, we take primary amine. So here aniline is a primary amine. So your aniline is treated with NaNO2 HCl. See, the temperature condition is 0 to 5 degrees Celsius. That is, cold temperature is maintained. And aniline is treated with these and to form a benzene diazonium chloride. That is, we will get BDC. That is benzene diazonium chloride. And then this diazonium salt, it is warmed with water to produce phenol. So here we'll use warm water. So look at this reaction. In this reaction, first we have a aniline. And when aniline is treated with NaNO2 in presence of HCl, we get a benzene diazonium chloride. That is BDC. Now you must have studied that how from a primary amine we will get a diazonium chloride. That is, diazotization is happening. So I'm telling you that here it is a primary amine, which is an aniline. So the reaction is that when your NaNO2 and HCl is reacted, you get NaCl, which is a salt, and HNO2. Then your HNO2 is treated with H+. And then you get a nitrosonium ion. And then this nitrosonium ion reacts with this aniline. It will attack on this aniline. And then you will get benzene diazonium chloride. You must have studied this process in your hydrocarbon reactions, hydrocarbon chapter of class 11. So this is how from a primary aniline you get a benzene diazonium chloride. Now when you get a benzene diazonium chloride, that is N2 plus and Cl minus, you will see that here warm water is taken. The water must be little bit warm. Okay, so your H2O will give H plus and OH minus ions. Okay, so now what will happen? Chlorine is a good leaving group, so it will leave from here with H plus. Okay, so chlorine will leave with H plus and it will form HCl because this chlorine is a good leaving group. Now see, this N2 will get a positive charge. Now nitrogen doesn't like a positive charge, so this N2 group will also leave from here. So see, this N2 group is also leaving. Now this carbon is an electron deficient carbon. Now what is left? OH minus is left. So this carbon is electron deficient and your OH minus oxygen has electron density to donate. So this OH minus will attack on this electron deficient carbon and you will get your phenol. And side products will be N2 and HCl. So this is how from a primary amine, which is aniline, you get your phenol. Okay, so first this aniline is reacted with NaNO2 and HCl, and then you get your benzene diazonium chloride. When it is treated with warm water, you get a phenol because chlorine is a good leaving group. It leaves with H+, and this nitrogen N2 group will also leave, making this carbon electron deficient. So OH will attack on this carbon and you will get a phenol. So this is a third method, that how from diazonium salts you will get a phenol. Now comes the fourth method of preparation of phenols, and that is from cumene. Now this is the most common method, or I can say an industrial method, from which your phenols are prepared. Okay, so here we will see that how from a cumene we will get our phenols. So first of all, your cumene is also called isopropyl benzene. That is, on a benzene, a isopropyl group is attached. That is called as cumene. Now this cumene is oxidized in the presence of air to form cumene hydroperoxide. So when you are taking this cumene and you are reacting in presence of O2, so you will get cumene hydroperoxide. Next, your cumene hydroperoxide is formed acetone and phenol on treatment with dilute acid. That is, when you treat this cumene hydroperoxide with a dilute acid, you will get a phenol and a side product which is called as acetone. Now, look, this is the process. First, we are taking a cumene. So, how from a benzene you will get cumene? You must have studied it in your class 11th, that when you take a benzene and you react that benzene with propene in presence of AlCl3, then you get a cumene group. Okay, that when benzene is reacted you take a benzene and a propene group, and in presence of AlCl3, you will see a cumene is formed. That is, this is an isopropyl group. That is, this carbon is further attached to two methyl groups. So then you will get a cumene. Okay, now this cumene is oxidized and cumene hydroperoxide is formed. See, at this carbon, two oxygen groups are attached and this hydrogen of this carbon only. Okay, so here your two oxygen group is attached and this is your peroxide linkage. This O2 is your peroxide linkage and this linkage is unstable. So when this linkage is unstable, it will break in the presence of an acid. So when you treat it in the presence of acid, you will see that this group, that is this CH3, CO and this CH3, this group will leave, that this acetone will leave, and we will be left with a phenol, that is OH, and here acetone is a side product, that is CH3, C double bond or CH3. So this is how from a cumene you get your phenol. So first we start with a simple benzene. You treat that benzene with propene in presence of AlCl3. You get a cumene. Now this cumene is further oxidized and you get a cumene hydroperoxide. That is this peroxide linkage. Now this peroxide linkage is weak. It is unstable. So since this is unstable, it will break in the presence of acid. So when you will treat this with acid, you will see this acetone group will leave and you will be left with phenol. So this is how from 4 methods we prepared our phenol. first method we saw from haloarenes, that is we took a chlorobenzene. From chlorobenzene we got a phenol. Next method we saw benzene sulfonic acid, that is SO3H group, which is attached to your benzene ring. By electrophilic substitution reaction taking place, you will see from benzene sulfonic acid you get a phenol. Next method we saw from diazonium salts. Okay, that is by diazotization you get N2 plus and Cl minus attached to a benzene ring, and then you get a phenol. Next method is the cumene, and this is the most common method or industrial method. Here from cumene, which is called as isopropyl benzene, you will see it is oxidized in the presence of air and a peroxide linkage will be formed. And this linkage is unstable. So when you treat it with acid, this gets break and you get your phenol and the acetone. So I hope all these three methods of the preparation of phenols is clear. Now let us solve some question. So this is in-text question 7.4. Now in this question, show how are the following alcohol prepared by the reaction of a suitable Grignard reagent on the methanol. So here you will solve this question that how alcohols can be prepared. So from this you will see that how alcohols are prepared by using a suitable Grignard reagent on the methanol. So I'm giving you some time. You take 30 seconds and you solve this question, and then we will discuss the solution of these questions. So your 30 seconds start now. Okay students, so let's see the solution. So solution says that whenever you are taking a methanol or a formaldehyde, you will see that primary alcohols are prepared. Okay, we discussed it when we were discussing about Grignard reagent. I told you there that whenever you are taking a methanol, that is a simple aldehyde, which is a formaldehyde, you will get primary alcohol. And if you take any other aldehyde other than your methanol, you will get a secondary alcohol. And whenever you take a ketone, you get a tertiary alcohol. Okay, so whenever, if in this case, in the question it is saying you have to react it with methanol. So methanol is a formaldehyde, you all know. So when you, in this case, your primary alcohols will be prepared when you are reacting it with a suitable Grignard reagent. Okay, and then when you react with the Grignard reagent, it is followed by acid hydrolysis. Hydrolysis, that means hydro means water and lysis means breakdown. That means you are breaking any compound in presence of water. That is called as hydrolysis. So first we will see the reaction of a Grignard reagent with a methanol. So see here, I told you whenever you take a Grignard reagent and here there is a methanol and adduct is formed. Adduct means an addition product of this Grignard reagent and this your carbonyl group. Here it is methanol. So see, I told you that this Mg is a metal, so it has an electropositive nature. So a partial positive charge will develop on this MgX group and partial negative charge will develop on this R group. And here we have a carbonyl group, that is C double bond O, and two hydrogens are being attached to this carbonyl group. Now you know that this oxygen is more electronegative. So if this is more electronegative, it will withdraw this electron density from this carbon. So when this oxygen will withdraw the electron density from this carbon, this oxygen will develop a partial negative charge and this carbon will develop a partial positive charge. So now who will attack on this oxygen? Oxygen O minus is there. So this here it is MgX, which has a partial positive charge. So this MgX group will attack on this O minus. So you will see OMgX is formed. And here your carbon has a partial positive charge and this R has a partial negative charge. So this R will attack on this carbon, which is electron deficient, because oxygen has withdrawn these electrons. So this R will attack on this carbon. As you see in this adduct, at this CH2 group, this R has attached. So this adduct is formed. That is addition product of your Grignard reagent and your carbonyl group. Okay, so this is the intermediate in this step. So next step, what will happen? Hydrolysis will happen. So this adduct will be treated with water. Now see, water gives H plus and OH minus. So what will happen? This MgX will have a positive charge, partial positive charge. So what will happen? OH minus will attack on this MgX group. So see MgOHX, separate this MgOHX. And your H plus has a positive charge and this RCH2 group. So your H plus will attack on this O minus over here. See, because this is adduct, it will form O minus and MgX will have a partial positive charge. So your OH will attack on this MgX and your H plus will attack on this O minus over here, because this oxygen has electron density over here. So H plus will attack on this, so it will form your primary alcohol, that is RCH2OH, and this group will be separated, that is MgOHX. Now see, whenever we are taking a methanol, you get a primary alcohol. How this alcohol is primary? Because the carbon to which your OH group is attached is further connected by one carbon only. So this alcohol is a primary alcohol. So this is how Grignard reagent, by using a Grignard reagent which is followed by hydrolysis, you get a primary alcohol in a case of a methanol. So these are the steps that needs to be followed. Okay. Now we will see one by one. We will solve for this question. And remember one thing, by varying the R group, different types of primary alcohols can be synthesized. If this R group is varied, then you will see that different primary alcohols will be synthesized. Now see the first part of this question. First part you will see that R is an isopropyl group. Okay, now we will see that how different R is varied and how we get different primary alcohols. So in first case, your R is an isopropyl group. When you look at this question, you will see that to this carbon, 2-methyl group is attached. So this is an isopropyl group. So first we take a methanol, which is a formaldehyde. To this methanol, see here, this isopropyl magnesium bromide is being reacted. Okay, when we will react to this isopropyl magnesium bromide, we will see a adduct is formed. That is the addition product of your methanol and this isopropyl magnesium bromide. So again, same steps will be followed. Okay, so what will happen? C double bond O. So carbon will develop a partial positive charge and oxygen will develop a partial negative charge. And here your Mg being a metal will get a partial positive charge and this R group, that is this isopropyl group, will get a partial negative charge. So this group will attack on this carbon, which is electron deficient over here. So see, to this your methanol, this isopropyl group has attached. Okay, and O has a minus charge and this Mg has a positive charge. So it will form OMgBr, that is this adduct is formed, and then this adduct will be hydrolysis will happen. So here your OH minus will attack on this MgBr, so it will form MgOHBr, and your H plus will attack on this O minus. So you will see a alcohol is formed, which is 2-methyl propanol. Okay, so this is again a case of a primary alcohol only, because the carbon to which your hydroxyl group is attached is further connected by one carbon only. See, this carbon is further attached by this carbon only. Okay, and the name is 2-methylpropanol. 2-methylpropanol, that is, we select the longest carbon chain. So this is the longest carbon chain. Since this has 3 carbon atoms, so the root word would be propane. And on first carbon, your hydroxyl group is attached. And see, on second carbon, a methyl group is attached. So 2-methylpropanol. Okay, so this was the first case that if your R is isopropyl group. So we got our alcohol from a simple methanol. And we are getting a primary alcohol only. Now let's see the second part of this question. In second part, your R is a cyclohexyl group. Okay, so this is a cyclohexyl group. So when you're treating it with methanol, this is your MgBr group and this is your R group. So again, a adduct will be formed. That is, this magnesium will have a partial positive charge and this group has a partial negative charge. And this carbon will have a partial positive charge and oxygen will have a partial negative charge. Okay, so this R group will attack on this carbon. So see your CH2O and your Mg will attack on this oxygen. So you will get this adduct over here. Now further you will break it in presence of water, that is hydrolysis. So your H plus will attack on this CH2OH and H plus will get attached to this oxygen. And your OH minus will attack on this Mg. So MgOHBr will leave and you will get a cyclohexyl methanol. Okay, which is a primary alcohol only. So this is a to this carbon, a cyclic group is attached. So cyclohexyl and methanol, one carbon. So methanol. Okay, so this is you get when your R is a cyclohexyl group. So this is how you saw that when you take methanol and you react with a Grignard reagent, then you treat it with hydrolysis, you get an alcohol. So whenever you are getting an alcohol, you will see that OL group is there in case of alcohol. That is the prefix we use in case of alcohols. Now, let us move to the next question. So write the structures of the products of the following reaction. So the reactions are given to you. You have to write the product of these reactions. So try solving it on your own and then we will discuss. So I give you 40 seconds for this question. You solve it and then we will see the solution. So your time starts now. Okay, students. So let's see the solution. See the first part. Now to this question, you will see that a propene is given to you, and when acid, what will happen? Your acid, which is S plus, it will protonate your double bond. Okay, and when it will protonate your double bond, you will form a stable carbocation at the secondary carbon. Okay, then you will see that the water, it will attack the carbocation, and then your deprotonation will gives the alcohol product. So these are the 3 steps that you need to follow for this particular question. Okay, so see the process. Here you have a propene. So when your acid, that is H plus, is attacking on this propene, so H plus, so you see you are having a double bond over here. So this H plus will attack and you will see that one of the carbon takes this positive charge and a carbocation is formed. Now you will see that at this carbon, your carbocation is more stable because this is a secondary carbocation. That's why at this carbon you see a positive charge and not on this carbon. Because on this carbon, your carbocation is not stable. You know the order for the stability of the carbocation, that is 3 degree, 2 degree, and last is 1 degree. Third one, 3 degree is more stable. So you will see at this carbon, because this is a secondary carbon. Why? Because to this carbon, 2 carbon atoms are attached. So this is a secondary carbon. So the carbocation will be more stable on this particular carbon. That is why at this carbon develops a positive charge. So your H plus will attack on this double bond, and you will see that this carbon develops a positive charge. So this is called a carbocation because it is more stable here. So this is a 2 degree carbocation. Next, what we will do, water will attack on this carbon which is having a positive charge. So what will happen? Your O, H and H, that is water, will attach on this carbon. Now water now you will see when your water will attach on this carbon, your oxygen will get a positive charge. Okay. Now further what's happened? You will get when water attacks again, you get a neutral alcohol. Okay. So this is propane 2-ol. That is, when if the water groups gets attached over here, the oxygen gets a positive charge over here. So when water will attack, and you will get a neutral alcohol. That is, your deprotonation will get your alcohol product. Okay. Now see this carbon. To this carbon, your other 2 carbons are being attached. So this is a secondary alcohol in this case. So this is the longest carbon chain. So the name will be propane 2-ol because at second carbon your hydroxyl group is attached. Okay. So this was the first case, that propene, when your acid, it will protonates the double bond. So it will form a stable carbocation at secondary carbon. And then when this water will see this positive charge on this carbon, this water will attack. And this water gets attached to this carbon. So oxygen will have a positive charge. So again, this water will attack and deprotonation will give you final alcohol product. Now let us see the second part. In second part, you will see that what will happen, it is given sodium borohydride, that is NaBH4. So what will happen, H minus, that is hydride from NaBH4, it will attack the carbonyl carbon of your cyclohexanon, because here you see cyclohexanon. This is a cyclic compound and in which there is a carbonyl group is attached. So when your hydride from NaBH4, it will attack this carbonyl carbon of cyclohexanon. It will form an alkoxide ion. And then what will happen? There will be protonation of this alkoxide ion and it will give you an alcohol. Now you will see in the question that ester group is also here in this. So this ester group will remain unchanged because we know that sodium borohydride is a mild reducing agent. So being a mild reducing agent, it cannot reduce this ester group. Okay, it can only reduce this carbonyl group. So what will happen? See this carbonyl group over here. Now sodium borohydrides give H minus over here. And you see that the carbonyl group, oxygen being more electronegative, will withdraw the electron density over here. So this will be C double bond O, oxygen more electronegative, so it will withdraw the electron density over here. So what will happen? This double bond, when your H minus will attack on this carbon which is electron deficient, so this double bond will break. So the electron density will shift on this oxygen. So alkoxide ion will be formed. Okay, that is to this benzene ring, O minus group is attached. And then your H plus will attack on this O minus and you will get a OH group over here. So this is your sodium borohydride reduced your carbonyl group. And you will see that this ester group over here remains unchanged because sodium borohydride is a mild reducing agent. Okay, because it is a mild reducing agent, so it will not reduce this ester group. Okay, let's move to the next question. Next question, you will see that again sodium borohydride is there. So hydride from your sodium borohydride, it will attack the carbonyl carbon of the aldehyde and it will form an alkoxide ion. And then further protonation of this alkoxide ion will give you a primary alcohol. So see over here, this is a 2-methyl butanol, that is this aldehyde group in the presence of a reducing agent, that is NaBH4. It will give you a alcohol, which is a primary alcohol. We have studied all these methods in preparation of alcohol. So sodium borohydride, it will give H minus. So this H minus will attack on this carbonyl group, that is C double bond O. So this carbon has a partial positive charge and oxygen negative charge. So H minus will attack on this carbon. So electron density will shift on your oxygen and this double bond will break. And then what will happen? The protonation of alkoxide will happen and you will get a primary alcohol. See, this carbon to which your OH group is attached is further connected by one carbon only. So this is 2-methyl butane 1-ol, because as second carbon your methyl group is attached. So this how aldehyde is reduced to primary alcohol in presence of a mild reducing agent, that is NaBH4. Now see the next question. You have to give the equations for you have to give the equations of reaction for the preparation of phenol from cumene. We studied it, that how from cumene you will get your phenol. So do this question. You have 25 seconds. Okay, so we see that how from cumene we get your phenol. So phenols, it can be prepared from cumene by aerial oxidation, which is further followed by the hydrolysis. So cumene, which is called as an isopropyl benzene, it is oxidized in the presence of air and it will give you cumene hydroperoxide. And then this cumene hydroperoxide, it gets converted to phenol and acetone by treating it with dilute acid. So see, this is cumene, which is isopropyl group is here. When you will do the oxidation of this cumene, you will see a peroxide linkage. And this peroxide linkage is unstable, so it will break in the presence of acid and it will form a phenol and acetone as the side product. We discussed it today itself. Next question, you have to write the chemical reaction for the preparation of phenol from chlorobenzene. This is also called as Dawes process. So write the reaction. I'm giving you 20 seconds. So see what will happen. Phenol, it can be prepared from chlorobenzene and that process is called Dawes process. So what happens in Dawes process? First you treat a haloarine. In this case we are taking a chlorobenzene with sodium hydroxide. So chlorobenzene is treated with NaOH at 623 Kelvin and 300 atm and it will give you a sodium phenoxide and sodium chloride. And then your acidification of sodium phenoxide takes place, where your sodium phenoxide is treated with HCl and it gives you a phenol. So this is a chlorobenzene you are taking over here. When you treat it with NaOH, chlorine is a good leaving group. It's leave with this H plus and Cl minus. And this is a nucleophilic substitution reaction. So a nucleophile attacks on this carbon, which is electron deficient carbon. So ONA will attack on this carbon and you will get O minus Na plus, that is sodium phenoxide. and acidification happens. So H plus attacks here, so it forms a phenol and NaCl leaves. So this is Dow's process. So let us summarize whatever we studied. We studied Dow's process, and this process requires high temperature and pressure. And we see that if there is an electron withdrawing group at ortho and para position, so it will make this reaction more easier. Next, we studied cumene to phenol. That was a commercial method. That is, it takes place in 2 steps. First, there is oxidation of cumene, and you form cumene hydroperoxide. That is the peroxide linkage. It is unstable, so it will break in the presence of acid, and it will give phenol and acetone. Next, we saw from benzene sulfonic acid, we saw that we use oleum for the sulfonation of your benzene, and this requires heating with molten NaOH. Okay, and then your acidification of sodium phenoxide ion, it gives you phenol. Next, we saw from diazonium salt method that it requires NaNO2 and HCl, and the temperature is low, and then diazotization happens, which is followed by warming in water, and then you get your phenol. So I hope this lecture is clear to you, students. Thank you.